Welcome everyone to Physics for All. I'm Shilpy Bhullar and we are doing video lecture series based on the topic vector analysis. In the previous video, we discussed physical significance of divergence. And now we have to understand divergence in terms of Cartesian coordinates so that we can use it mathematically in our derivations. So let's get started. Here, as you can see in the graph, we have taken a cuboid. And then again, as we are talking of divergence, so we need a vector because this del operator, the divergence, can only be found of a vector. So we consider a vector field A, and of course that vector field would be present in this entire region. Okay, so this is the entire region where this vector field A is present. And then to solve, obviously we are going to consider some small element from that region. Here, a vector A is basically a velocity vector. It represents velocity of the fluid. Some fluid is flowing through the space, through this region, and that velocity of the flow of the fluid is considered to be a vector. We know velocity is a vector, so that is what our vector A is. It is a velocity vector. And we are concerned with the velocity of the fluid at center P. As you can see, this small dot, and here we have taken the point P, and it is within an infinitesimal element of volume. Infinitesimal means very small, extremely small. So in the whole region, it's very difficult to find any value over the entire region. So what do is we consider a small element from that region, and now we have chosen a volume element. As we discussed divergence and its physical significance in the previous video, we saw that divergence is concerned with surface which encloses some volume, because ultimately divergence is all about the spread or how much a particular vector is converging. But definitely it would be encompassing some area. There would be some area involved, and that area might be enclosing some volume as well. So whenever we talk of divergence, just keep in mind that the two main aspects out of three, which are line, surface and volume, two out of these three are surface and volume, which would be of importance when we talk of divergence. Because divergence talks about how much something is spreading or converging. So there would be two-dimension and three-dimensional involvement as well, because we would see how much something is spreading or converging over a particular surface, and that surface, if it is a closed one, it would be enclosing some volume. That's why whenever we talk of divergence, the two quantities, the two aspects involved would be surface and volume always. Whenever you find surface and volume, think of divergence. This we have considered a small element of volume in the form of cuboid. You can see the cuboid here, and it has its sides. This is dx, which is the side BC, and dy, side DE, and then dz is the side CD. So they all are parallel to x, y and z axis. Obviously dx, dy, dz, they represent a very small change in the x component, y component and z component respectively, because we have considered a really small volume element. Now since this vector A is a velocity vector, so this velocity would be having its components along all the three directions. You know, whenever we express any vector, we express it in terms of all the three components along all the three directions. Like vector A is what? It is always written as ax I cap plus ay j cap plus az k cap. So here ax is the component along x-axis, ay is the magnitude, you can say, along z-axis, and az is the magnitude along, ay is the magnitude along y-axis, and az is the magnitude along z-axis. So this is the general representation of any vector. Similarly, if we have a velocity vector, so it would be having its velocity components along all the three directions. So for V, we can consider Vxi cap plus Vyj cap plus Vzk cap. So Vx is the magnitude of velocity along x-axis, Vy is the magnitude along y, and Vz is the magnitude along z-axis. So same we have shown here at point P. You can see we have drawn the arrows. This is the Vx magnitude of velocity, and Vy and Vz, they all are magnitudes of the velocity vector along all the three directions. So to find the expression of divergence of a vector in terms of Cartesian coordinates, let's start. Now we have this cuboid, we have this small volume element, and we know that the vector being chosen here is the velocity vector of a fluid. Some fluid is flowing. So let us consider that the fluid is flowing through these two faces ABGF and CDEH, which have been highlighted in blue. You can see. So these are the surfaces. All the sides of a three-dimensional figure, they are basically surfaces, areas. Now this ABGF, it doesn't include or enclose any volume. It's simply a side, it's simply a surface, it's a two-dimensional figure. And same is for CDEH. They both are the sides of cuboid. The whole cuboid, A, B, C, D, E, F, G, H, this whole cuboid is a volume element, but all the sides involved, if you talk of the top and bottom, the left and right, the front and the back sides, they all are surfaces. Thus here, these two faces, ABGF and CDEH of this volume element, they have area dy dz. Yes, is it true or not? Because you can see there is no involvement of x direction here. It's kind of slanted, this AB side and the CD side, same for GF and HE. You can see that they represent Z direction because Z axis has been drawn laterally. You can see that. And then this BG, AF and CH, DE, they are vertical lines. So they represent y-axis, but there is no representation of x-axis. GH, FE, AD, BC, they are representing the change in x-axis. But here the faces that we have considered, they do not represent change in x-axis. They only represent change in z-axis and y-axis. As you know that something from AB is going to GF, something from CD is going to EH. So there would be some change in Y component. And then you can say that something which is AF is going to BG or something which is ED is going to CH. So definitely there is some change in Z component. So that's why they have area d by dz, and which is definitely perpendicular to x-axis, as we are talking of coordinate system where all the three x, y and z axes are perpendicular to each other. Thus, the value of x component of this velocity vector v at the center of face, if you talk of this at point Q, whatever is the Vx, you can say whatever is the x component of velocity vector at Q, that will be different from what is that at P, because we are considering a vector, velocity vector, and vector has both magnitude and direction. Even though the direction is same for Q and for P, direction is same, we are talking of x direction only, but the magnitude is changing. You can see if something is at Q and it suddenly moves and go and reaches P, there would be some change in x. The x component would change. So overall, we would say that the vector present at Q would be a bit different than the vector present at P. and that difference arises in terms of x component only, because from q to p there is no change in z component, there is no change in y component. That's why this x component of v at center of face ABGF, that is point Q, will be different from the x component of V at P. Now let's see what is that difference. If the fluid is flowing like this direction, if we are considering about this x-axis and this is the way this velocity vector is flowing, so whatever is the value of x component of V at Q, that will be different from the value which is at P. And then again from P to R there would be some change as well. Now suppose this fluid is now again moving from P to R, so change in Vx, and here this Vx represents magnitude. Since we have not written any arrow overhead, so this is a magnitude and basically the x component of velocity, right? So this change in Vx in going from P to R, because there is no other change, there is no change in Vy and there is no change in Vz, only Vx is changing. What would that be? Now you can see here, in going from this P to R, what is the change? Obviously Vx would be changing because there is some change in x-axis, and you also see that this whole thing is dc and p is at the center, so the distance from p to r would be dx by 2. So this is the clear-cut change that we can see, that the distance, the only change in x-axis or x component in going from p to r is dx by 2. This is the value. And then obviously the way this velocity vector depends on x-axis, it would change its value. Thus this change, we would write it as curly Vx upon curly x. Now you can see why we have written curly here, because ultimately this Vx is not an independent vector. The vector is V, which is depending on all the three x's. This V is depending on x-axis, y-axis and z-axis, because it has component along all these three axes, and whenever there is change in those axes, the value of V would change. And that's why we say that this velocity vector is partially depending on all the three directions, on all x, y and z. And that's why we have to use curly, because curly is specifically meant for partial differentiation. So this is the thing, this is the change in Vx because it is changing with respect to x. And also we are saying that there is change in distance as well. If you say, and that is dx by 2. From P to R, we have dx by 2. This is the thing. We started from ABGF and ultimately the fluid is going out from CDEF. This is what we considered. We considered the flow of fluid through two phases which have been highlighted in blue. So fluid entered through ABGF and it is coming out through CDEH. So the change, or we can say the value of x component, if we are concerned with the value of x component of V at center CDH, that means at point R. Now we want to know what is the value of x component of V at point R. So for that, what do we have to do? We have to take the value of x component of V at P, and then increase in the value of x component of V from P to R. This is the thing that we have to use. So if we write here the x component of V at P plus the increase in this value from P to R. Now what is the value of x component of V at P? We consider that at point P, the components of vector V are Vx, Vy and Vz along all the three axes. So x component is simply Vx. So here we can write down Vx, and then what is the change or what is the increase in it? Obviously, because this flow is along positive direction of x-axis. Okay, this is positive direction of x-axis. So the value would definitely increase. Value of x is increasing. So the increase in it from P to R is what? This line that we have written, the change in Vx in going from P to R. So this is the basically the increase. So here we can write it as half curly Vx by curly x and then dx. As we know that this point R, which is at the center of CDEH, is on the right hand side of point P, and this point Q, which is at the center of ABGF, is on the left hand side of point P. And this dx is, since P is at the center, so we can say that the distance QP is also dx by 2. Okay. So here we have this QP is also dx by 2 and PR is also dx by 2 since P is lying in the middle. As we have found the value of R, whatever is the value of Vx at R by using P, the value at P, in the same way we can find the value at Q also. The only difference is that Q is lying along the negative direction of x-axis with respect to point P. With respect to point P is important. Q lies along negative direction of x-axis with respect to point P. Although this point Q is in the positive region. See, this origin is here and whatever figure we have drawn in the positive xy region. Because if we go to the left of origin, then we have negative values. But here we are saying that Q lies along negative direction of x-axis with respect to point P. This point P is important, that we are talking in terms of point P. Whatever approximations we are taking with respect to point P. So either something is lying to the right of point P or something lying to the left of point P. So either something is in the positive direction with respect to P or something is in negative direction with respect to P. So for that, what we can do? We can again use this thing, that x component of V at P, but whatever the increase is definitely there from Q to P, but that would be with a negative sign. Here I am going to write this directly, Vx, because we need the point, the value at P, minus half of curly Vx by curly x dx. That would actually give us decrease in the value. This actually giving us decrease in the value of Vx from Q to P. Or you can say either way, like this also represents increase in the value from Q to P, but since we are considering P as a reference point, so either we are looking toward the right of P or we are looking toward the left of P. So this value is same, but the only difference is that Q is lying along the negative direction with respect to P, and that's why we have to write minus sign. Otherwise everything is same. See, the x value, x component of V at P is always Vx, that we already know, and the increase would also be curly Vx by curly x. Okay, because what we know is Vx. So curly Vx upon Vx, and again dx by 2 will also be there because QP and PR both are dx by 2. P is lying in the middle. But the only difference is that we are going to write negative sign here. This provides us the value of x component. That means only one dimension is involved. As you can see in both these values, the value that we have found at point R and also at Q, we have simply the x components. Here we have Vx, and then we have curly Vx by curly x and dx. So you can see that only x components are involved. But if we want to find the volume of fluid flowing through the phases that we have considered per unit time, then for that we need two more directions. We consider these two phases. We have got the x component because we know that via these two phases, the only change that was occurring was along x-axis. Only the change in x component was occurring when the fluid was flowing through these phases. But we want to know what is the volume of fluid passing through these. What is the volume of fluid entering in and coming out of these two phases? For that, for volume, we need three dimensions. So what do we have to do? We have to multiply with the two extra directions, and those should be dy and dz. And now you can see here we wrote that the flow of fluid through the phases ABGF and CDEH of volume element, each with area dy dz, because these phases they were having area dy dz. As you can see, these faces look like parallelogram, and parallelogram has area as we simply multiply. Sometimes we write it as base into height, but here we can simply multiply the two sides, the length of the two sides. And what is the length of these two sides? That is dy and dz. This is also dy, this is dz. So this is the area. We already know what is the area of ABGF and CDHE. This is the area, dy dz is the area, and we already know what is the quantity or what is the change in x-axis. So simply we have to multiply all these three and we will get our volume element, the flux entering the volume element ABGF in x direction, because this is given by product of normal component of velocity of fluid on the face and area of the face. We know the area of face and we also know the product of normal the normal component of velocity, which is Vx. Here I am going to write this is Vx for point Q, which is at the center of ABGF. So this is the value of x component. We already have one component with us. And then to get the volume, we have to multiply with the area. And area of these two faces is dy dz. So this is how we have obtained. We have found flux entering the volume from left face. Now we want to know the flux leaving the volume through the right face, and that would be whatever is the value of x component at point R that we have found here. This is the value, and into the area, which is again dy dz. So this value would be Vx plus half curly Vx by curly x dx multiplied by area of the face, which is dy dz. Now the excess of flux leaving the volume element over that entering, we want to know the difference. Always when we talk of a vector which is just passing through a particular surface or some volume, most of the time we are concerned with the change, with the difference, that what is the difference? Is the amount entering equal to amount leaving, or if there is any other difference? When we talk of divergence, as we discussed in previous video, that we have either zero divergence or we have positive divergence or negative divergence. In positive divergence, we have sources present which actually increase, which diverge or spread out the vector. In case of negative divergence, we have sinks present which actually converge it. So the volume which was initially flowing is not equal to the volume which flows finally, or which flows after going through the sink. And in case of zero divergence, the amount of flux initially and finally both remain the same. So even if we know how much flux is entering, and we know how much flux is leaving, but that really doesn't matter. What is of more concern is that what is the difference? Is there any change happening or not? We are always concerned with the change. For that, we have to find the change. So let's find that. We can write Vx plus half curly Vx by curly x dx, and then we have this dy dz minus Vx minus half curly Vx by curly x dx, and again there is dy dz. Because whenever we find the flux, we always subtract the initial value from the final value. Here we have to subtract the incoming flux from the outgoing flux. We have to subtract the entering flux from the flux which is leaving. If we do that, what do we get? Let's see. Here we get Vx and then dy dz plus half curly Vx upon curly x dy dx dz, and then here we have these two terms. Now you can see this Vx dy dz, and here we have again Vx dy dz but with a negative sign. So these two will get cancelled and we are left with, and these are half and half, so that would give us 1. So we have curly Vx upon curly x dx dy dz. This is the actual difference in the flux. So do you think that's it? Is it over? Do you really think so? Or do we need to do something else? Well, of course, we are not done yet, because we have found the change in flux only through these two faces, which are right and the left face. But initially, we considered volume element, we considered a cuboid. So we have to discuss what is the change occurring from top and bottom, and what is the change occurring from front and back. Because fluid is going through all the surfaces, so there would be some change in all the directions. We have this top and bottom face as well, and then front and back. So I'm not coloring the front and back because then it would be a bit difficult. But see, you can see the top and bottom colored in orange. We have to find the flux through all these faces. In the same way, we can find the flux leaving along y direction. So can you tell me which of the faces would be involved for the change in flux along y direction? Well, y represents this vertical distance. So whenever there is vertical change, we call it the change along y direction. Here you can see that this face, the bottom face, is almost similar to the top face. And if liquid is entering from the bottom face and it is going through the top, obviously there is change in y. And you can see z and x are not changing. They are having same value. And also the area of these two faces, A, B, C, D and E, F, G, H. The area is what? It's dx dz. Here also dx dz. So this is the area. Now we will not solve it again because then it becomes too lengthy. The way we did here, so whenever you derive, solve it for one direction, and then you can just write it down that similarly for the two directions, because everything is same. All we have to do is just replace x by y. Here we were talking of x, now we will be talking of y. And if x is getting replaced by y, then the dy and dz will also be replaced. From here the answer we got was, the final answer was curly Vx upon curly x dx dy dz. So that means when you consider the change along x direction, this is the thing, this quantity matters. Rest you will get all three directions involved. You will get dx, dy, dz because we started with this thing, but but dy and dz got multiplied. So overall in the answer we have dx, dy, dz, but the only thing is this is special, this is different, that curly Vx upon curly x. So if we talk of y direction now, if we talk about the changes or the excess of flux leaving the volume element over that entering in y direction, then what do you think would be the difference? Dx, dy, dz will still be there, but instead of curly Vx, we would be having curly Vy upon curly y because we are considering the change along y direction. So let's write it down. So along y direction, this would give us the answer curly Vy upon curly y, and this would be the same dx, dy, dz. So this is also done. Now which direction is left? Z direction. So let's solve for that too. For z axis, what would be the faces involved? Can you tell me? Which faces are left? Obviously, we have 6 faces of cuboid. We have talked about 4 faces. Only 2 are left, and they are the front and the back. So this front, which is BCHG, and the back one. Let me show it with different color. The back one is ADEF. So these are left now. Again, the way we wrote for y, we can write in the same way for z axis, because now this dx, dy, dz would be same, but the only change would be along or would be in the z component. So instead of curly Vy upon curly y, we would be having curly Vz upon curly z. And you can see that here in both these faces, the change is occurring along z axis. See, this is the z axis, as you can see, and they are inclined in such a manner that one has to move through along the z axis to go from this front face to the back face. So the liquid will move along the z axis to go from the first face to the back face. And again, there is no other change. The area of these two faces are, this represents dy and this is dx. Same here, this is dx and this is dy. So area is dx dy. This we can write here directly, curly Vz upon curly z, dx dy dz. Now our work is done. We have talked about all the faces, all the 3 directions. Now what is left? Of course, we have to see the total effect. So the total flux leaving or diverging, as we can use this word, from the volume element. Now we have to write that. As we use phi to represent flux, and this symbol was first introduced when we studied magnetic field, we used to write phi is equal to B dot A. Here also to represent the total flux leaving, that means the total change in flux by d phi. And this word diverging, see, usually we don't know how the liquid or the fluid will perform. But here, by default, we always talk of positive divergence. Since we are talking of divergence in terms of Cartesian coordinates and we have to look for the expression of divergence. So if divergence is 0, then there is no question of talking of divergence. And negative divergence is also not used that much. We don't talk about it that much, though it is there. In general, by default, we always talk of positive divergence, and that's the reason why I have written here diverging from the volume element. We are saying that once the liquid enters in and then the moment it comes out of the cuboid, it will just diverge. We are considering the case of positive divergence for our convenience because that is easy to solve. Now for the total flux, all we have to do is just add all the flux, all the change in flux that we have found along all the three directions. So they were curly Vx upon curly x, dx, dy, dz, and then we have the y and the z terms, and we can combine them because dx, dy, dz, they are just common in all the three terms. This value obtained is basically the net volume of fluid flowing out per unit time from the volume element. So this is the entire expression which tells us how much, what is the net quantity of liquid flowing out from that volume element which was a cuboid. Thus the divergence of vector V is basically the total outward flux per unit volume from point P, because we considered volume element and the point considered was P. We found everything with respect to P. We took P as our reference point. So total outward flux would be whatever value we have obtained here, that is the d phi per unit volume, because volume is important. That would actually give us the idea of divergence in a better way, because from that we would get to know that what was the volume available and then how much is the spread. So the spread is always with respect to the volume that we have considered. That's why this is the d phi we have obtained, but the divergence would be d phi upon dv per unit volume. Then how to do that now? And divergence of vector v, so definitely I can mention it as del dot v. And now d phi by dv. First of all, here we have used d phi. Why? Because now this phi includes all the terms. So that is the complete, the total change in phi. And it is changing with respect to volume. So that's why that is also dv. There are x, y and z involved, all the three direction involved, but in general the total quantity is dv. And there is no other partial dependence. That's why we have considered d. So if this is d phi by dv, and we can take this dx, dy, dz to be dv, because ultimately it is the product of the changes in all the three directions, all the three lengths, the change in all the three lengths, all the three sides, and that would give us the change in volume, because volume comprises of three sides, three lengths are there. So thus if we divide d phi by dv and this dx, dy, dz is our dv, we would be left with this quantity is left. And that's the reason we always mention the divergence of any vector like this. We discussed mathematically, we discussed with physical significance, and now combining both the things, both that mathematics and the physical significance, we have understood divergence in terms of Cartesian coordinates, which tells us that whenever we have any vector, in general any vector, and we have to take its divergence, why do we get this? When first we discussed divergence, we were just told simply that this is the expression for divergence. Whenever we have to find divergence of any vector, we have to write this. This would be our final result. But then by understanding the physical significance and then finally understanding divergence in terms of Cartesian coordinates, we now actually understand that how do we obtain these terms? How do we obtain the divergence of any vector as these terms as our final result? Because all other terms got cancelled and what was left was these three terms. Obviously, it is a scalar quantity because we are not seeing any I cap, j cap or k cap here. And now this topic, this present topic that we have done, this actually justifies the expression of divergence of vector. The expression that we just learned before, now we know how did it come. So this is all about divergence and its significance and its meaning in Cartesian coordinates. Now we will use this divergence in understanding a very important theorem, which is Gauss divergence theorem, in the next video. Till then, keep watching, keep subscribing. and keep learning physics. Thank you.